All right, so we have a seemingly long lesson today, but it all kind of goes together. It all flows together. There's not a whole lot of really difficult stuff. I'll try to get through the technical stuff as quickly as we can, and we'll kind of see the application of it. Hopefully, kind of shine through here. So. Today's lesson is all about scatter plots. Okay, scatter plots. Okay, so scatter plots are used to visualize the relationship between two numerical variables. They are used to analyze data to look for potential relationships. Okay. So anytime we're collecting data, if it's a survey or whatever it may be, I don't want to say never. We will rarely get data that is in an exact straight line. Right? That's not real world. Generally, there are different people do things differently. There's going to be some variation. There may be some people that don't follow the same trends as other people. Okay, if you're collecting data on some kind of object rather than a person, there are always different kinds of variables related, right? Like wind, time, space, blah 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 blah. Okay, pressure, all kinds of things that can make something not flow in an exact straight path, and that's okay. Because we have scatter plots that we use to look at data, look for trends, see how strong a relationship is, different things like that. Okay? Okay, so let's consider the following three scatter plots. I want you guys to go ahead and do questions 1, 2, and 3 together with your group. So you're looking at those three scatter plots. Answer questions 1, 2, and 3 together with your groups. Ready, set, go. Okay, what'd you guys say for number 1? Does there appear to be a relationship between X and Y from scatterplot 1? Yes. Okay, cool. We agree on that. Let's expand on that a little bit. So let me ask you kind of a few questions that you can kind of think about. Feel free to raise your hand and we can kind of answer these. Does the relationship appear to be linear, quadratic, or exponential? Raise your hand if you can answer that question. Does the relationship appear to be linear, quadratic, or exponential? What do you think, Will? Linear. Yeah, it does appear to be linear, right? Starts low, takes off high. Let me ask you another follow-up question. Does this relationship appear to be positive or negative? What do you guys think? Positive, right? Because this relationship would have kind of a positive slope, right? It's increasing. That means it has a positive relationship. So last question, does this scatter plot appear to have a strong relationship between the two variables or a fairly weak relationship between the two variables? What do you guys think? Strong? I'd say that's a pretty strong relationship, right? It pretty closely follows the same pattern, okay? All right, let's move to number 2. So give me a thumb. Does number 2 appear to have a relationship between X and Y? Give me a thumb, yes or no? Ooh, I see some yeses and nos. Anybody care to elaborate? Yeah, Juan? You said yes, right?
Yeah.
Okay, what do you think?
I think they do have a correlation, just there's an outlier in there.
Very good word. Okay, so there's this thing called an outlier, right? So, you honestly, with a scattered plot like this, I would want more data points, okay? Because I could see a couple things happening here. I could see what Juan said, it being kind of a linear relationship with an outlier, right? This one up here. Or, what shape does that kind of look like? the U shape. What do we call that U shape? A parabola, right? So that would be a quadratic. I could see this kind of relationship happening. Okay, so in that case, I would definitely want some more information, right? Because the more points that I get on there, the better I'll be able to tell, is that just an outlier or does it look like a quadratic? Okay, good. All right, let's look at 3. Does 3 appear to have a relationship, yes or no? Thumb, give me a thumb. Yes or no, does it have a relationship? Yeah, I think most of us are saying no. I would agree. This kind of doesn't really have a relationship, right? I can't tell if the data is increasing or decreasing. I can't tell if there's any kind of linear pattern or anything like that. I'll be honest with you guys. For the most part, the scatter plots that we're going to look at will either have a linear relationship or no relationship. It starts to get a little more tricky when you're looking at a quadratic scatter plot. So for the most part, we'll be sticking with linear or no relationship at all. Okay, so let's go down here and fill this in down to the bottom. Okay, so kind of what we're getting at, knowing if there's a relationship or not, knowing how strong it is, knowing if it's positive or negative, all of these things can be found by one very easy number called a correlation coefficient. Okay, so a correlation coefficient. Okay, so a correlation coefficient. So it says it's a summary statistic used to describe the strength and direction of a linear relationship. 2 things that we just talked about. Okay, all right, let's look at how we determine the course page. Okay, all right, so what I want you guys to do now is I want you to answer 4. So actually, you're going to do this whole page. I want you to answer 4 and 5 together with your groups. So you are going to kind of disregard, in the first time through, you're going to disregard these R numbers down here, okay? And you're just going to match the graphs based on the wording. So very strong positive linear relationship. Which one of my graphs represents the strongest positive relationship? 7. So then I would put 7 here. You go down, you do all, how many are there? 7 of these. So you'll do all 7 of these. And then you'll go back and look based on, okay, so strong means I have this kind of correlation coefficient. Relatively strong means I have this kind of correlation coefficient. And then I want you to answer questions 5, A, and B together with your groups, okay? So you're doing all 4 together, then go back and look at your R values, and then try to answer 5 together with your groups. Ready, set, go. Okay, so here we go. All right, so we went from very strong to relatively strong. So which one's a little weaker but still a pretty strong positive relationship? 2, I would agree with that. Okay, then we move, what's wrong with my pen? There we go. Then we move to relatively weak positive linear relationship. What do you think? 4? Yeah, I'd agree with that. Oh, sorry, Efren. When I was helping you, I couldn't see the numbers. I gave you the wrong answer for that one. Very slight or no relationship. Which one do you think that would be?
3.
Yeah, 3 looks like the closest one to having no relationship at all. Relatively weak negative relationship. What do you think? 6. That's good. Relatively strong negative relationship. 1, yep. And then the very strong negative relationship. 5, good. All right, so looking at my R values, let's answer number 5. So it says, what determines if R is positive or negative? This is not a trick question.
The negative side of front.
Okay, you took that a little too literally. Okay, so what could we say about the relationship? This is kind of hard since we haven't talked about line of best fit. What do we call it when a line is increasing? What is positive about that line if it's increasing? Come on, guys, focus. What is positive about the line if it's increasing? Think about the equation of a line. What's positive about it if it's going up? The slope, right? So that's kind of what determines if R is positive or negative. A positive slope. So a positive slope is going to produce a positive R. Okay? A negative slope is going to produce a negative R. Okay? So we can tell if a relationship has a positive relationship, or if a relationship has a positive correlation, that gives it a positive R. If it has a negative correlation, it has a negative R. Okay? What determines if R is closer or further from 0? What did you notice about the ones that were really strong?
They're like grouped together and going up.
I know. What did you notice about the R values of the ones that were really strong?
They were bigger.
We got to be careful with the word bigger. What were they closer to? 1 and... What about the really strong negative ones? They were close to -1, right? What about the ones that were really weak? What number were those close to? Closer to 0, right? Okay, so weak is close to 0. Strong is close to 1 or -1, depending on if it's a positive or negative relationship. Okay, so you have positive, you have negative, and then you have either. So everybody look at me really quick. We have close to 0, this is weak. The further out you get to 1 or -1, that's when you get stronger and stronger and stronger, right? As far as your R values go, okay? So we have to be able, let me give you a little preview, okay? Desmos, when we start plotting scatter plots on Desmos, it will spit out an R value. So you do not have to be able to calculate the R value, but you have to be able to interpret the R value. You have to be able to look at R equals 0.8 and tell me that that is a positive, relatively strong correlation. Or a positive, strong correlation. You need to be able to look at -0.2 and tell me that that is a negative, weak relationship. Okay? Those are the things you have to be able to do once Desmos spits it out. Okay? All right, let's keep rocking and rolling. Let's go to my next. Ooh, what is happening? What just... Okay, so we've talked about correlation. Now let's talk about the line of best fit. Okay? So you can see it said one of two ways. You can either say trend line or line of best fit. Okay? So you can have either one of those. They mean the same thing. Trend line and line of best fit are the same thing. It is the line that best represents the relationship of the data on a scatter plot. The reason the line of best fit is helpful is because it will then help us predict. Okay? So scatter plots are not only good for giving us data on this current stuff that we have, but if we are trying to predict, that's the best way to do it, is to find the line of best fit and then be able to predict using that line of best fit. Okay? So what I want you to do is start with number 6. Okay? So start with number 6. So tell me, on the scatter plot 1, would this be a good line of best fit? No. Why does that not fit the data? Why does that not fit the data? They're all above the line, right? Same thing if I put the line up above. That would not be a good line of best fit. Is this a good line of best fit? I have half above and half below. Is that a good line of best fit? No, that's not. Why is it not a good line of best fit? Doesn't really follow the same general shape as the data, right? Okay, is this a good line of best fit? Getting closer, right? But still not following the same shape. So I would want to get about half of them above and below, and I want to follow the same shape, right? There's no perfect science to drawing your own line of best fit. As long as you can get pretty close, I'm okay with it. Okay? Scatter plot 2, am I going to have a positive or negative line? Positive, right? And it's going to be following this same general shape. Scatter plot 3, can I draw a line of best fit on that? I mean, it would just basically be guesswork. That would be my best guess. It's a really weak relationship, but it looks a little more negative than positive to me. Same thing with 4. Looks a little more positive than negative to me, but it's still a pretty weak relationship. Okay. Okay, so we talked about reasoning of where to draw our line of best fit. Let's go ahead and look at 8 together, okay? So it says consider scatter plot 4, okay? It gives us the equation of the line of best fit. So again, when we plug this stuff into Desmos, Desmos will spit out some numbers that will allow us to write the equation of the line of best fit. What you have to be able to do is interpret it, okay? So if it spits this equation out and it tells me that, let's see, X is age, Y is shoe size, okay? And then it gives me the equation Y equals 2/3 X plus 1. So describe what the slope and y-intercept mean in context of the problem, okay? So what is the slope in this equation? 2/3, okay? Remember, a slope is how the data is changing. So when we are interpreting slope, we always want to put it in kind of a if this, then that kind of statement. Or for every blah, this happens. Okay? So let's describe it in terms of age and shoe size. Okay? So I'll start it, you guys finish it. Okay? For every year a child grows, how would I finish that? Based on shoe size and based on the slope of 2/3. So for every year older a child gets, what happens? Their shoe size increases because it's positive by 2/3 of a size, right? So that's what I would say. I would say, so let's go ahead and write that. Just so we have an example in our notes here. So for every let's just say year older. For every year older, a child's shoe size increases by 2/3. Okay? So for every X, Y happens, right? For every X, Y happens based on the slope. How would I interpret the y-intercept? What are you born with? Feet! Congratulations. Okay? You're born with feet. So, on average, that would basically just mean that the beginning size of a child's foot at birth would be 1. Okay? So, size at birth averages, or is, let's say, is 1 on average. Is 1 on average. Okay, so there's my slope and my y-intercept. All right, we want to predict the shoe size of a child when they turn age 6. So it gives me age 6. What do I do with that 6? Put it in where? X or Y? Which one? What's it tell me up in the problem? It says age is X. So I need to plug it in for X. Okay? So I have Y equals 2/3 times 6 plus 1. So remember, fraction times a whole number. I multiply the tops, divide by the bottom. So on top, 2 times 6 is 12. 12 divided by 3 is 4. And then add the one more, so y equals 5. Change pages. That probably just totally screwed up my video. Sorry if it screwed up my video. So we get y equals 5. So that would be their shoe size when they turn age 6. Okay? C, a very interesting question. Would the data in equation be useful to predict the shoe size of an adult age 40? You don't think so? Why not? Okay, so we know that your feet stop growing after a while, right? You always have to take into consideration the scope of your survey. If you are only surveying children, it doesn't always make very good sense to extend that out to adults. Okay? It would probably, honestly, if you're looking at shoe size over a lifetime, it's probably more of like a exponential decay, right? Kind of like that kind of relationship, because it grows real fast when you're young and then it kind of levels off, right? So it might look more like an exponential decay. Okay. All right, let's get into some nitty gritty. And then we'll be done. Okay? So we have looked at everything we need to look at. Okay? Now the only other thing we need to do is learn how to put this into Desmos. So say you are given a what am I trying to say? Say you are given data, and you need to be able to plug it into. You need to be able to pull data from it. Sorry, I'm trying to pull up my camera really quick so I can take a picture of this scatter plot. Because I'm going to be flipping back and forth here for a little bit. Okay? All right, I got that. So say you are given data, and you need to be able to determine different information from it. Okay? There is a very easy way to use Desmos to do this. Okay? But it gets slightly technical, and you will have to know how to do this on your test. Okay? So there will be a portion of this test where you have your graphing calculator out, and you're using Desmos. So make sure, I know sometimes when you do stuff on the calculator, it's like, yeah, that's really cool, but I'm never going to be tested on that, so you don't really pay that close of attention. This you will be tested on, okay? So make sure you're paying close attention here, okay? So I'm going to pull Desmos up really quick and show you what we're going to do, and then I'll bring it back to this screen so that you can have this scatter plot up there so you don't have to flip back and forth 100 times, okay? So everybody open up. So I'm going to go ahead and pause the video. I'm going to show this, and then I'll start it back once we start pulling data. Okay, and we're back to the video now. Okay, so just as a very fast recap, we went to Desmos. We input our table. We use y. The equation y1 is approximate to mx1 plus b. So when we use that approximation equation, Desmos spits out information for me, right? So Desmos spit out R equals 0.3034. It spit out M equals 0.312. And it spit out B equals 39.57. Okay, 39.57. Okay, so those are the three numbers I care about from Desmos. Now let's go ahead and answer my question. So what is the correlation coefficient? Remember, that's R. So that's going to be 0.3034. And then we want to interpret what the correlation coefficient implies. So you need to be able to tell me two things about the correlation coefficient. Is it positive or negative? That should be the easy one. Oh my gosh. Is the number positive or negative? It's positive. Okay, good. And then is this a strong or weak relationship if it's 0.3? That's pretty weak, right? The closer it is to 0, the weaker it is. Okay? So I would say this is a weak, positive relationship. Okay, it's a weak positive relationship. Okay. All right, C says, what is the equation of the line of best fit? So remember, this is y equals mx plus b. So now I can go ahead and plug in my m and my b that I got from Desmos. So y equals m is 0.312 x plus b, and b was 39.57. Okay. So I apologize. I was so quick to jump into Desmos that I didn't really look at the context of this problem. So let's go back up really quick, because in order to tell what the slope and y-intercept means in the context of the problem, we're going to have to actually know what the problem is about. So it says the data set below shows price in dollars and quality rating for 12 different brands of bike helmets. Okay, so price is X, quality is Y. So for every blah that happens, this happens. For every dollar price thing that happens, quality is going to do this. Okay, so let's go ahead and put that in context. So we have a 0.312 slope. So I start with for every X. So for every $1 increase, what is the Y that results? What does Y represent? Quality. So the quality, does it increase or decrease? Is it positive or negative? Positive, so it's going to increase. So the quality increases by, what's the slope? 0.312. All right. So for every $1 increase, the quality increases by 0.312. So for every $1 increase, the quality increases by 0.312. Okay, and then it says, what would you predict the quality rating for a $75 helmet to be? Okay, so I would want Y, my cost, equals, oh yeah, X is my input, right? So Y, my quality rating, equals 0.312 times the money value that I'm plugging in of 75 plus 39.57. Okay, let's go ahead and do that. Oh, what's going on here? There we go. So 0.312 times 75 is 23.4 plus 39.75 is, so the quality rating is going to be 63.15. 63.15. And I think it said 0 is the worst, 100 is the best. So you got an above average helmet for $75 as far as quality rating goes. Okay? So let's just recap really quick, okay? We have lots of information flowing around in our brains right now, okay? We have correlation, right? So that R value that Desmos spits out allows us to tell if the relationship is positive or negative. It also allows us to tell if the relationship is strong or weak, okay? That's what that correlation coefficient tells us. And then we also have a line of best fit. That line of best fit is the line that is supposed to accurately depict the scatter plots relationship. Okay. Again, Desmos will spit out a slope and a y-intercept for that line of best fit. Line of best fits are great for predicting. Okay, that's the main reason that we use line of best fits. Number one, so we can get a more accurate portrayal of what the relationship is doing. And number two, to be able to predict, just like we did. If I am willing to spend $75 on a helmet, I should expect to get a quality rating of 63.15 out. So you go to the store, right? You go to the store and you find a helmet on the shelf and it is $75. You look at the tag and the quality rating is 45. Should you buy that helmet? No, you're getting ripped off, right? You're not getting what you're paying for. You may be paying for a brand name. You may be paying for just somebody that thinks that they can run the cost up on you. But you know right then and there, based on this data, for $75, you should be able to get a helmet that is quality rated at 60, whatever it is, 63. If you go into a store and you find a helmet that's $75 and the quality rating is 75, you know you're getting a good deal. You should buy that, right? As long as it's nice and pretty and matches your bike, right? Because that matters. Okay. No laughs? No even like pity laughs? Nothing? Thank you. Okay, cool. All right, guys. So lots of information. The only way we're going to be able to process it and keep it into our brains is by practicing. So let's do that. Ready, set, go.